chapter 16, Introduction to Oscillatory Motion and Waves. So there are at least 4 types of waves in this picture. There's the waves on the water, but there's also sound waves coming from this guitar. There's light waves, coming from the fire. And there's waves, standing waves on the guitar string. And we're going to talk about these kinds of things. But we're going to start with oscillations. Of course, there's the typical overproduced physics video called harmonic motion.
Like to experience it from an entirely different perspective.
Sports. I don't know why these videos offend me so much. I feel like it's like they're trying to say, we all know physics is boring, but if we shout a lot and talk about sports, it's actually not so bad. So I feel like physics is what it is, and and this chapter actually about waves is a pretty good one, and oscillations. So let's get right into it. If you can see this ruler I've got here, this ruler, I've just got it so that it's pointing up, and it has an equilibrium position in the middle. If I push it to the side, it wants to spring back to the middle. But when it does so, it overshoots the middle, and it ends up oscillating back and forth. So that's a nice example of what's called oscillatory motion. And where it all starts is Hooke's law, which we've seen before. The force is on the object that's being deformed somehow, restores it to its equilibrium position. X is how far it's being displaced from its equilibrium, and K is some constant. And the negative sign here, I think they put a negative sign here because it's trying to remind you that if X is in one direction, F is in the opposite direction. So it looks a little different than before. We've still got this force constant, and the way we would plot it here is there's a linear relationship between how far something is from equilibrium and the force that restores it back to equilibrium. So K, rise of a run, is a constant here. So I guess, for example, if you hang a mass on a spring, pull it down, the spring wants to pull it back up to some equilibrium position. Also, if you compress a spring, it wants to push it back down. And when you think about the energies, you have potential energy that's in the spring, this elastic potential energy, and as something's moving, you have kinetic energy, and if something's oscillating, then you're transferring energy from the spring into kinetic energy and then maybe back into the spring. So next section is just defining something called frequency. So we define periodic motion to be a motion that repeats itself at regular time intervals. The time to complete one oscillation is constant, and it's called the period, capital T. Its units are usually seconds, but it could be any convenient unit of time. The word period refers to the time for some event, whether repetitive or not, but we shall be primarily interested in periodic motion, which is, by definition, repetitive. And a concept closely related to period is the frequency. So, if you get a paycheck twice monthly, then the frequency is 2 per month. So you're dividing by time. Frequency is defined to be the number of events per unit time. So for periodic motion, the frequency is 1 over the period. And there's a unit for frequency, it's 1 over seconds, also called hertz, 1 cycle per second. And they give some examples of which, if you know the period, you can find the frequency, or if you know the frequency, like you know that middle C is 264 hertz, you can find the period is 3.79 milliseconds of a sound that's at middle C. Section 6.10.3 is called simple harmonic motion, a special case of periodic motion. So simple harmonic motion, SHM, comes from when an object has Hooke's law. So example would be a spring, which one end is connected to a fixed wall, the other end is connected to a mass, which is resting on a frictionless surface. So when the spring's in equilibrium, we call that x equals 0. That's where the mass doesn't get pushed one way or the other. If you stretch the spring, there's an acceleration pulling it backwards. If you compress the spring, there's an acceleration bringing it forwards back towards 0. So it oscillates back and forth. And there's a periodic motion with a period, which is equal to 2 times pi times the square root of m over k, where m is the mass of the object in the spring and k is the spring constant. So there's a good equation which could go in your aid sheet. It's not derived in this textbook, but once you've got the period, you can take 1 over that to give you the frequency. So this is 1 over 2 pi, and instead of m over k, it's k over m. And what's interesting is neither the period nor the frequency has any dependence on amplitude. So it's a little hard to picture that, but they actually have a pretty nice PhET animation at the bottom of it. There's some graphs, I guess, of position versus time. You get this kind of wavy shape. It turns out to be a cosine curve. What you can do is take these masses and kind of hang them on the spring and let them go. So if you take the same spring constant and hang different masses, you do increase the mass, for example, and let it go. Whoa. So it goes a lot farther here. I think this one just has a lower equilibrium position. Whoop. But you can see the period for the larger mass is longer, so that's square root m over k. And if you make the two masses the same, but you change the spring constant, so you put a higher k value, then the period goes down. Or a weaker spring, the period goes up. And what's interesting too is that what we'll do is we'll start one with a large amplitude and the other one with a small amplitude. 1, 2, 3, go. So what's interesting here is that if you can see it, this one's moving a lot faster, but it's going farther. So the period is the same no matter what the amplitude is. So remember, period, capital T, is 2 pi times the square root of m over k. It depends on the mass, depends on the spring constant, but it doesn't depend on the amplitude. So if it goes faster, it still goes through a full oscillation in the same amount of time. And last section is the simple pendulum. What they're showing here is that if you just hang a mass m from a string, from a ceiling or something, and pull it to the side, it'll naturally swing back and forth. And this is a type of simple harmonic motion. So they kind of show you a derivation of the restoring force here. It's negative mg sine theta, but sine theta, if theta is small, is approximately equal to theta if you use theta in radians. So rearranging the numbers here a little bit, you get F is approximately equal to negative mg divided by L times S. So since mg and L are all constants, it kind of looks like this negative kx, where instead of s, you've got x, its position, and then you've got some constant. So this expression is of the same form as Hooke's law. So even though it's a pendulum, we think that it moves with simple harmonic motion. And you kind of substitute the same variables. Instead of having m and k, you've got L and G, and the m's go away here actually. So the period of a pendulum is 2 times pi times the square root of L, the length of the pendulum, divided by G, which is just 9.8. And you can play with the PhET animation here. Turns out that if you change the mass, like a really big mass or a really small mass, it doesn't change the period of the pendulum. But if you change the length, the smaller length oscillates with a shorter period, the longer length oscillates with a longer period. Energy and the simple harmonic oscillator. So they start with the example of a mass attached to a spring. The other end of the spring is attached to a wall. As the mass moves, the spring stores potential energy, elastic potential energy, 1/2 kx squared, where x is the position away from equilibrium. And because a simple harmonic oscillator has no dissipative forces, the other important form of energy is the kinetic energy. And the kinetic energy plus the potential energy is a constant. And in this case, 1/2 mv squared plus 1/2 kx squared is constant. Now, that's for the mass attached to a spring. If you have a pendulum of length L, so this L here, it's not angular momentum, it's the length of the pendulum, then the velocity is that length times omega, and the displacement is length times theta, and instead of adding potential energy from the spring, you add the gravitational potential energy. It all turns out to be this equation. So how does it all work exactly? Well, it's actually coming from cosine and sine. The x is equal to the amplitude times cosine of 2 pi t over t. So when the mass is far from equilibrium, all of its energy is 1/2 kx. Where here capital X is meant to be the amplitude. And then when it passes equilibrium, Vmax is the maximum speed. So you can find the total energy to be when the speed is 0, and that's when x is at its maximum, as it's at the amplitude, so 1/2 kx squared. And that allows you to solve for the speed at any other time. The speed being either plus or minus, so we can be velocity is plus or minus k over m times the amplitude squared minus x squared. So at the points where x equals the amplitude, this goes to 0. And this is a way of finding the maximum speed and how it relates to the amplitude. And then there's an example here. And in this example, they use a whole different letter for amplitude. They use lowercase a. So the maximum speed is 2 times lowercase a times pi over t. This next section is basically just pointing out that the function for simple harmonic motion is the same function, or mathematically the same, as one component of uniform circular motion. So maybe the horizontal component. So for example, if you have an object that is going in a vertical circular path at a constant omega, or constant rate, constant period, and you were to shine a vertical light down and look at the shadow would move back and forth with simple harmonic motion. And it's pretty easy to find that. Here, capital X now is the radius, the constant radius of this circle. If you look at just the x component, lowercase x, it's this amplitude radius times cosine theta. And theta is equal to omega, which is the constant angular velocity, times t. And so this equation, x is equal to the amplitude times cosine of 2 pi t over the period, is exactly the same equation that we had for simple harmonic motion. But in this case, it's now just the x position of a point going on a circular path at a constant speed. So it's a nice little trick, really. Section 16.7 is about damped simple harmonic, or damped harmonic motion. So I guess simple harmonic motion has this property that it goes forever. A sine curve or a cosine curve goes up and down, and the amplitude stays constant for all time. In real life, any oscillation, the amplitude of it, this capital X, is going to slowly decrease with time due to friction and loss of mechanical energy to like thermal energy. So this graph is what is called underdamping. So it's basically simple harmonic motion with a steadily decreasing amplitude. There are some situations, like the suspension of a car, which is holding up the car on springs, in which you don't want it to bounce and bounce. So there's something called critical damping, is defined as the condition in which the oscillator returns to its equilibrium position as quickly as possible. That is this curve A. And then if you increase the damping even more, you can get an overdamped system here in which it slowly returns to equilibrium. And lastly for today, section 16.8 is about forced oscillations and resonance. So in 16.7, you had a harmonic oscillator in which the energy was being taken out of it gradually by friction. Here we have a harmonic oscillator in which energy is being added somehow. So the key here is that there's something called a natural frequency. The natural frequency is just the frequency at which a system would oscillate if there was no driving or damping force. And so that's exactly what we've been studying in this chapter so far. It's just the oscillation frequency. But resonance happens when you have a periodic driving force. So some external force is happening with its own frequency called the driving frequency. And when the driving frequency matches the natural frequency, when it's equal to the natural frequency, this is called resonance. And a system that's being driven at its natural frequency is said to resonate. As the driving frequency gets closer to the natural frequency, the oscillations become higher. So here's a driving frequency that's lower than the natural frequency. There's a bit of an oscillation there. When the driving frequency equals the natural frequency, then it oscillates a lot. When the driving frequency is a bit higher than the natural frequency, then again the amplitude goes down. So here's a plot of the amplitude of oscillations versus the frequency, where F0 is the natural frequency. You get a peak there. And depending on the amount of damping, you can have a driven and damped oscillator. You can get a sharper peak for how high the amplitude goes when you're matching the natural frequency. An application of this is this suspension bridge built in 1940, the Tacoma Narrows Bridge, has its own natural frequency that it tends to oscillate at, and that there were gusts of wind that were actually interacting with the bridge itself, and these gusts began to circulate and create a driving frequency. And unfortunately for this bridge, the driving frequency of these gusts of winds matched the natural frequency of the bridge, and the whole bridge collapsed. It's section 16.9 on waves. So when you hear the word waves, you normally think of water waves. Here are some surfers or some boats and a great big wave coming along. Well, that's one example of a wave, but there's lots of kinds of waves in physics. In physics, a wave is a disturbance that propagates or moves from the place it was created. So for water waves, the disturbance is on the surface of the water. For sound waves, the disturbance is a change in air pressure, perhaps created by oscillating the cone inside a speaker. For earthquakes, there's several types of disturbances, including pressure waves and shear waves. Radio waves are waves in the electromagnetic spectrum, as is light and X-rays. So they talk about a misconception alert. Many people think that water waves push a bunch of water from one direction to another. In fact, the particles tend to stay in one location, save for moving up and down due to the energy in the wave. And at the end of this section, there's a link to this PhET animation. And I think it's a little easier to see on an animation than in a diagram. Here's a wave, and if you kind of blur your eyes, you see the whole wave moving from left to right here. But if you look at any individual particle, for example, this green one right here, look at that. It's only moving up and down. It's shaking, but it's staying in place. It isn't moving from left to right at all. It's the pattern of this wave, this cosine wave actually, which is moving along from left to right. The distance between two adjacent crests in a wave is called the wavelength, and the symbol for wavelength is lambda, the Greek letter lambda, which looks like that. And then as any particle on the wave oscillates up and down, it has an oscillation period. And it turns out that the speed of the wave, the transverse speed of the wave, or how fast those crests or troughs are moving along, is equal to the wavelength divided by the period. And since the period is 1 over the frequency, or the frequency is 1 over the period, the speed of the wave can also be given by the frequency in hertz multiplied times the wavelength. There's an example of using that. And then they talk a little bit about transverse waves. That's what we've been studying so far. And another thing called longitudinal waves. This is a terrible little drawing, but once again, I have an animation which is a little better. This is sort of a not to scale, zoomed in drawing of a bunch of air particles. So sound, which is what this is modeling here, is a longitudinal wave. So over here on the left, you see a speaker which is oscillating left and right. And what that is doing is pushing air particles to the right, and when it goes to the other direction, it's kind of creating a vacuum, and maybe some of those particles are kind of rushing in to fill the void. And if you blur your eyes now, what you see is darker stripes and lighter stripes moving from left to right here. So that's what one of the characteristics of a longitudinal wave is, that there's regions that have high density and regions that have low density. The high density regions are called compressions, because also the pressure is higher there, and the low density regions are called rarefactions. So compressions and rarefactions move away from this oscillating source. And if you look at any particular particle, it is oscillating in place, and it is oscillating parallel to the direction that the entire wave moves along. And so, for example, if you have, here's a guitar, it's hooked to an amp, and it's making sound. So the strings oscillate up and down with some frequency. That gets amplified at the same frequency, and then a sound, the speaker oscillates with that same frequency, and that makes a sound wave which goes out into the air, travels some distance, gets to your ear, and oscillates your eardrum, at that same frequency, and that's how you hear the guitar string. 16.10 on superposition and interference. And they open up with this picture of waves that result from the superposition of several waves from different sources. So one of the big differences between particles and waves is that if two particles end up at the same place at the same time, they will collide and bounce off each other and interact. Waves, on the other hand, if two waves end up at the same position at the same time, they will just pass right through each other. And in fact, when they are at the exact same position at the exact same time, you simply add the displacement of one wave to the displacement of another wave. And if they're both positive, then they add. If one is negative, then of course they subtract, and you can have canceling of waves. So this is called superposition. And in fact, there's something called constructive interference and destructive interference. So here's an example of constructive interference. You have wave 1, and it is added to wave 2. So these two waves exist at the same place for some reason. Well, in that case, what will happen is that at this point, for example, this wave plus this wave, they're both in the same direction. You'll double the amplitude. If it's x, you'll have 2x. And then when they're 0, they'll be 0. When it goes down to negative x, they're both negative x, the resultant wave will have negative 2x. So you end up with a very similar wave, but now the amplitude has doubled. This is what's called pure destructive interference. That is when you have two waves and they're identical in every way. Identical in amplitude, identical in wavelength, identical in frequency. But what's different about them is that they're offset by half a wavelength. So if two waves are offset by half a wavelength, then when the crest of one wave arrives, the trough of another wave will arrive. So you've got plus x minus x, you get 0. And that's also true. It's when the trough of the first wave, it encounters the crest of the second wave. So you get negative x plus x, you get 0. So the resultant is just 0. You get, if these were two sound waves, you'd have silence. But there are lots of other types of superposition. You could have waves that have different frequencies and different amplitudes. Here's a low frequency, high amplitude wave plus a high frequency, low amplitude wave, and you get this kind of wiggly thing. So this is just added at every point to this. So you get that same up-down shape, but with a bunch of wiggles. And this is important because this is exactly how sound works. If you hear two sounds at the same time, you get the superposition of both sounds hitting your eardrum, and you can end up distinguishing both of them by somehow analyzing all of those frequencies, which is really important if you're listening to music and you're hearing different instruments at the same time. They all get combined in the same wave that hits your ear. The next part is about standing waves. So there's something called standing waves, which is a result of superposition. And it comes up quite a lot in physics. The way you get it mathematically is you add two identical waves, identical in amplitude, identical in wavelength, identical in frequency, but they're now traveling in opposite directions. So here wave 1 is traveling from right to left, and wave 2 is traveling from left to right. And one of the most important examples of this would be a wave plus its echo, its reflected wave. And in that case, what happens is alternately you get constructive and then destructive interference. Constructive, destructive, constructive, destructive, constructive, destructive. And so you get a pattern which kind of stands there and goes up and down. And there are certain properties of standing waves, such as nodes. So there are nodes on standing waves that never oscillate at all. It goes up and down here. That's called an antinode. And then right here, there is no oscillation. And here you can see something called the first overtone, where you have an antinode about a quarter of the way between two fixed ends. You have a node at each end, and you have a node in the middle. You can also have a second overtone where you have two intermediate nodes, and what do they call loops here? These are antinodes, so 3 loops. That's second overtone. So these are also called harmonics. This is sometimes called the second harmonic and the third harmonic. And the last thing this chapter or this section talks about with superposition is the phenomena of beats. And so this is when you have two waves with maybe similar amplitude, similar frequency, but not quite the same frequency. So F1 and F2 are different, but just by a little amount. So they might start off with constructive interference, but every time there's a cycle, since the one frequency is slightly different than the other, one of these waves starts to lag behind until at some point the troughs of one correspond to the crest of the other, and you get destructive interference. But then it continues to lag until another wavelength goes by, and you end up with constructive again. So it goes constructive, destructive, constructive, and every time it goes to constructive interference, you hear the volume increase. So it goes woo, 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 and kind of beats like that. And there's something called the beat frequency, which is equal to the absolute value of the difference of the two beats. So if you have a frequency F1 and a frequency F2, and you subtract them, you get the frequency of how many times per second you hear these constructive interference beats. And the last section of chapter 16 is talking about energy in waves and a phenomenon or a property of waves called intensity. So certainly waves carry energy from place to place. Here is the destructive aftermath of an earthquake, which is a wave in the Earth's crust that goes along and shakes everything in its path, causing massive amounts of destruction. So waves carry energy. And it turns out that for almost all waves, the energy carried along by the waves, which we're going to call intensity in a little bit, is proportional to the amplitude of the wave squared. So if you double the amplitude of a wave, you tend to increase its energy it carries by a factor of 4. So how do you quantify energy? There's power, that's the amount of watts or amount of joules per second that are delivered by the wave, but then in 3 dimensions, a wave will have also a cross-sectional area. So how much power is delivered per cross-sectional area. So intensity is that power in watts divided by the cross-sectional area in meters squared, and you get watts per meter squared. So sunlight is carried by light, which is a wave. And here on Earth, the sun delivers about 700 watts per meter squared intensity of light. So if you had a solar collector that had a particular area of 0.5 meters squared, then you would multiply that, you get 350 watts would be how much it would absorb. And there's something interesting which you might have noticed is that, remember, with perfect constructive interference, the amplitude doubles of 2 waves right side by side, which means that the intensity goes up by a factor of 4, which is a little disquieting, as they say, because, for example, if 2 individual waves have intensities of 1 watts per meter squared, that's the energy. If you add them up and they constructively interfere, you'll get 4 watts per meter squared, which is double the amount of energy you started with. It was 1 plus 1 is 2. Instead, you get 4. But what's interesting about that is any 2 waves will have what are called fringes. Some of the areas are constructive and some of the regions are destructive, and they average out so that the destructive goes to 0. You've got 1 plus 1 equals 0, so that's about half the time, and the other half the time 1 plus 1 equals 4. And the average of 4 and 0 is 2, which is the amount of energy you started off with. So the fringes do end up conserving energy. And that is it for chapter 16. Bye for now. My name is Jason Harlow, and I hope you enjoyed this video. If you have time, please fill out the feedback form on my Google Forms available in the description to this video. There's also a link to the Google Classroom where there's a public discussion forum and a place where you can ask me a lot of questions. Also available as a link in the description to this video. I look forward to hearing from you. Take care.